Hello, calculus students. This is Mr. Allen. Today we are going to look at section 2.6, which is on something called related rates. So we're going to see really nice application of what we've been doing in chapter 2. Our objectives here are to find a related rate, and 2, to use related rates to solve real-world problems. So I'm going to do 3 examples today and also try to explain this process to you. The chain rule can be used to find dy dx implicitly. Another important use of the chain rule is to find rates of change of 2 or more related variables that are changing with respect to time. In fact, I'd like to highlight that in our study, this particular section, almost all the derivatives we're going to do are going to be with respect to time. So for example, let's say that water is being drained out of a conical tank, as we see here on the right side of this diagram. The volume V with the radius R and the height of H of the water level are all functions of time. Knowing that these 3 variables are related by the equation volume equals pi over 3 R squared H. So that's a formula for the volume of a cone. You can differentiate implicitly with respect to time t to obtain the related rate. So here in the red, you can see the formula that we just did. And now what we're going to do is we are going to do the derivative of those things with respect to t. So we're going to need to do the chain rule. So the derivative of v is going to be dv dt equals, now don't forget that pi over 3 is a constant, so we can pull that out to the front, and we're going to have r squared dh dt plus h times the quantity 2r dr dt. Now, in case you're not sure where this came from, this is the product rule. So we have the product of 2 variables, r squared and h. So that is the product rule along with the chain rule. So then we can clean that up and we get the following expression for dv dt. From this equation, you can see that the rate of change of the volume is related to the rates of change of both the h variable and the r variable. So let's look at an example. This is a simple one, but it'll kind of illustrate the points of how we work with these related rates. It says, suppose that x and y are differentiable functions of t and are related by the equation y equals x squared plus 3. We're asked to find dy dt when x is equal to 1, given that dx dt is equal to 2 when x is equal to 1. So that sounds like a lot of information, but we need all of it to actually be able to come up with a final answer. So the first thing we got to keep in mind, as we do with all of these related rate problems, is we're going to need to use the chain rule to do the derivative of our original equation with respect to t. So original equation is y equals x squared plus 3. We do the derivative of both sides with respect to t. Using the chain rule, we're going to get dy dt equals 2x dx dt. Now keep in mind the derivative of 3 is 0, so that's why that's not in play in this particular problem. Now if x is equal to 1, which is given up here in the original problem, when we know that dx dt is 2, we can plug those things into our differential equation right here. And so that's going to tell us that dy dt is equal to 2 times whatever x is, which we said is 1, times whatever dx dt is, which is 2, and that's all given information. So the answer is 4. So dy dt is 4 when dx dt is 2 and x is equal to 1. So here are some steps for trying to solve related rate problems. I'm going to do 2 more actual applications. That last one was pretty contrived. So first thing you want to try to do when you're doing these problems is identify all the given quantities and quantities that need to be determined, and try to make a sketch and maybe label some of those quantities on that sketch. Number 2, you want to write an equation involving the variable of whose rates of change either are given or are yet to be determined. Then don't forget to use the chain rule to differentiate both sides. This is the most important step in terms of calculus. And remember, we're going to do our derivative with respect to t. And then after completing step 3, you're just going to substitute known results in to figure out what it is you're trying to find. So here's my second example, which is on inflating a balloon. Now we are going to assume that the balloon is perfectly spherical. So it says air is being pumped into a spherical balloon at the rate of 4.5 cubic feet per minute. So that is a derivative. The rate of change of the radius, find the rate of the change of the radius when the radius is 2 feet. So they're telling us that radius is going to be equal to 2. We're asked to find the rate of change of the radius at that moment. So the first thing we do is we're going to let volume be written in terms of R, which you're probably already aware of. We know that the rate of change of the volume is 4.5 cubic feet per second. Or in other words, we could say that's 9 over 2. So the dV dt is 9 over 2, same thing as 4.5. We know that we can express this, and this is a constant rate. In other words, the amount of air that's going into the balloon is not changing. It's going constant. Somehow we're magically just pushing that exact same amount of air in constantly. We're also told to find dr dt when r is equal to 2. So all I've done here is I've basically said, here's what we're given, and here's what we need to find based on r equaling 2. So now let's go ahead and look at our formula that we're going to need. So this is another key step, is you need to know what the formula is for the volume of a sphere. Hopefully you remember that that's 4/3 pi r cubed. And now we're going to do that key third step, which is to differentiate both sides of this equation with respect to t. The derivative of v with respect to t is dv dt. On the right-hand side, there's only one variable, so that's the only thing we need to worry about. Remember that 4/3 pi r cubed, the 4/3 pi r cubed, that is just a constant. And so then when we do our power rule with r to the third, the 3's are going to end up canceling out. So that's why you're left with 4 pi r squared, and then don't forget the dr dt. Now, we are trying to find the dr dt, so let's go ahead and solve for dr dt, and by this we're just basically cross multiplying, and so we'll get 1 over 4 pi squared dv dt. And now since we are given that the dv dt was 4.5 or 9 over 2, this is a very simple question now. We can simply plug in what we know. Don't forget here there was another variable down here of r squared, but remember r is 2, so we're just going to take that squared and take that times 4. That's where the 16 comes from. And we get a final answer of roughly 0.09 foot per minute. In other words, the radius of the balloon is changing at 0.09 foot per minute when the radius is 2. So this is a related rate question, and that's the answer. Got one more example and then we'll be done. So example 3 is about hot air balloons. So I've got a picture here of a hot air balloon that I basically snatched off the internet, and I've got a right triangle, which we'll talk about in a minute. And it says that we're given that the theta, that's this angle here, this angle here is pi over 4, which is the same thing as 45 degrees, but we're going to do it in radians. In this class in general, you almost everything do it in radians. And then I'm also giving you, should have put a comma there, that the d theta dt is 0.14 radians per minute. In other words, what I'm saying is, first of all, it's positive, so this getting larger. I'm saying that the change in the angle measure is 0.14 radians per minute. In other words, the balloon's going up, so the degree is increasing. So the question that I would like you to answer is, how fast is the balloon rising? How fast is the balloon rising? So you can pause the video and see if you can figure that out. But I'm just going to go ahead and move forward. So we're asked to find dh dt. We're asking to find how fast the height is changing with respect to time. Well, we could use a very commonly known ratio for tangent, which is opposite over hypotenuse, opposite being h, and adjacent, I think I said that incorrectly. Let me try that again. Tangent is opposite over adjacent. I think I said hypotenuse, and that's incorrect. Tangent is opposite over adjacent. So the opposite side from theta would be h. The adjacent side would be 500. So tangent theta would be equal to h over 500. Now we can go ahead and differentiate both sides with respect to t. So let's start with the right-hand side, this h over 500. You could think of that as 1 over 500 h. So the derivative of that with respect to h is 1 over 500 dh dt. Now the right-hand side, this comes back to knowing your derivative rules. The derivative of tangent is secant squared theta. But then we also have to include the d theta dt by the chain. Now we can go ahead and substitute in what we know. Well, what is d theta dt? Well, that was given up here. That's 0.14. What is theta in this problem? Well, that's pi over 4. So instead of theta here, I can put pi over 4. Now I'm going to add one extra little detail here, because basically what it's asking me to do is find the secant of pi over 4. So you got to remember that secant is the inverse, or reciprocal, I should say. There's reciprocal of cosine. So if we're talking about pi over 4, then the secant of pi over 4 turns out to be radical 2 over 1. So in this case, we need to substitute radical 2 in for the secant of pi over 4. So that's going to be the square root of 2 squared. We can clean this up and multiply it out, and you will get exactly 140 feet per minute is going to be the rate at which the balloon is changing its height. So this is a nice application of using the chain rule, implicit differentiation, to solve real-world problems like figuring out how fast the balloon is moving up. I think that's it for this presentation, so we'll go ahead and stop it there. Thanks for your attention.